Alright, hopefully you have tried this on your own before coming here. If not, stop, take 10 minutes, try this on your own, then come back and check. Alright, first few. Speed is a scalar. It does not include direction. Velocity is a vector. It does include direction. Acceleration is a vector. It includes direction. And force is a vector. We can add forces just like vectors, as you even did a lab on with the force boards. Force is a vector. Something you might want to note is that the net force is always in the same direction as the acceleration. Same. Because a net force, according to Newton's second law, causes an acceleration as acceleration. And that's because F net, or a net force, equals mass times acceleration. So in a problem, they might ask you which direction is the acceleration, and that's whatever direction the net force is. So if I gave you these two forces, 10 newtons to the left and 10 to the right and 3 to the left, and the problem said what direction is the acceleration would be to the right because that's the direction of the net force. Similarly, if there were some problem where you knew the acceleration were pointed down and the problem said which way is the net force, well, the net force would be in the same direction as the acceleration. So if you knew the acceleration was pointed down, the net force would be pointed down as well. Next problem, what is a newton? Well, a newton is a measure of force, and force comes from F equals mass times acceleration. So that's F equals, and if we do this by units, mass is kilograms, acceleration is meters per second squared. So a newton, the unit for force, would be kilogram times meters divided by seconds squared, which is answer A, kilogram meter per second squared. Okay, this next question is not something we've talked a lot about. It says if you need to break a force into components, where should you not do this? You should not do it on the free body diagram. So whenever you draw a free body diagram, that's only forces. So a free body diagram is only forces, not components. So for example, if I had a block on a ramp, it would be acceptable for me to draw, say, the weight force and the normal force and friction, but it would not be acceptable for me to draw weight and the x part of the normal force x, and y part of the normal force, I guess it should be F and y. You don't break vectors into components on your free body diagram. You do it somewhere else. This is not something I've ever suggested you should do anyway, so you wouldn't do it. Just know that on your free body diagram you only draw forces for real. So here you would draw the actual forces and not their components, friction, weight, and the normal force. But you wouldn't, on the diagram, divide them up into components. What are two types of motion in which you can set the up forces equal to down forces and left forces equal to right forces? Answer in simple language as if you were explaining to a fifth grader. So the first time I can set something up equals down and left equals right is for an object that's not moving. Or maybe if I'm talking to a fifth grader, I should say something that's not moving. Or something moving at a constant velocity, or maybe for a fifth grade, something going, or something whose speed doesn't change, something that doesn't change speed. Doesn't change speed. That would be both equilibrium, but one would be static equilibrium and one would be translational equilibrium. So, and that's number 8. What are the two situations called in which you set up forces equal down forces and left forces equal right forces? Answer using proper physics terms. The two situations are static equilibrium and translational equilibrium. Okay. Okay, for questions 9 and 10, so that's these two. A block with mass m is placed on a ramp making an angle theta with the horizontal. I've left some space down here so I can draw this. So our block of mass m is placed on an angle theta. And it says after the coordinate axes are tilted, so let's draw them tilted. I'll have y, and I'll have x. What is the vertical component of weight? Write your answer in terms of mg and theta. Okay, so let's real fast draw the forces on here. We've got a weight force straight down. We've got a normal force at a right angle to the ramp. And we've got a force of friction parallel to the ramp, going against the way the block would want to move. So if the block were to move, it would slide down the ramp. Friction opposes motion, so it points up the ramp. The vertical component of the weight. So vertical is the y-axis. So vertical component, that's the y-axis. The y component of the weight would be this part here. And we've talked about before that this angle here is theta. The vertical component of the weight is adjacent to that angle, so that would be Fg cosine for adjacent theta. Problem says answer only in terms of mg and theta. So that would be mg cos theta. And there's our answer in terms of mg and theta. We found the vertical component, the part on the y-axis. Next it says what is the horizontal component of the weight? Well, horizontal is the part on the x-axis, and so that would be right here, the part of that triangle opposite the angle. Since that's opposite the angle, that'd be Fg sine theta, and we're only allowed to answer in terms of ng and theta, so mg sine theta. That is the horizontal component of the weight. Moving on to number 11. Notice that number 11 is not part of the drawing. The question says for questions 9 and 10, so we've already done those. Number 11 is by itself. That could be confusing. You might try to solve for number 11 from the drawing. Write the equation for the force of friction. Well, that's pretty easy. Force of friction is F equals mu times the normal force. And then on the mu, you would put either S or K, depending on static or kinetic. But since the problem just said force of friction and didn't specify, I'm going to leave it like this. FF equals mu, the coefficient of friction, times the normal force. And you should, by now, have memorized that equation. If you haven't, go do it. Other equations you should have memorized: Fg equals mg, Fnet equals ma. Sure, on the free response you'll have an equation sheet, but multiple choice you won't, and you'll save time if you're not scrambling to look for those equations. So these three right here, you should definitely have memorized for this unit exam. All right, moving on to page 2. If an object has balanced forces on it, what is the net force? Well, balanced forces means forces in x equal forces in negative x, forces in y equal forces in negative y, or as we have said, up equals down and left equals right, so our net forces are 0. If an object has balanced forces acting on it, what is the acceleration? Well, you could just remember balanced forces mean no acceleration, or you could come back to F net equals 0 and say, well, that's mass times acceleration. The mass of an object's not 0, and if I solve for acceleration, I'd find A equals 0, divide by m, I get A equals 0 over m, which is 0. So acceleration is 0 when forces are balanced. If an object has unbalanced forces, it by definition has a non-zero net force. So unbalanced forces means there is a net force. Unbalanced forces also mean there's an acceleration, so non-zero acceleration. And you can see that again, if F net is bigger than 0, and you tried to solve for ma, you would get A is bigger than 0. Probably a little confusing there on the math, but if you just remember unbalanced forces cause an acceleration, that's what Newton's second law says. If you think about F net equals ma, the way I teach this in CP is a net force causes a mass to accelerate. So unbalanced forces cause acceleration. Alright, a person is standing in an elevator that is moving upward but slowing down. So let's think about that for a second. The elevator has velocity upward, but it's slowing down. That means it's accelerating the other way. In order for the velocity to get smaller, your acceleration would have to be the other way. So its acceleration is down. Draw and label a free body diagram for the person. Okay, so the person has acting on them their weight, and there's a normal force from the elevator. Now the elevator has a tension because there's a string, but the person has weight, and the person is standing on something, and because he's standing on something, that's a normal force. The elevator has tension, the person has a normal force because he's standing on something. Do the forces in your diagrams have the same magnitude? If not, state the larger force. Well, there is an acceleration. The person's slowing down. There is an acceleration. So one force has to be larger. Now, which one? Well, the acceleration points down because slowing down would mean you're accelerating opposite your velocity. So your acceleration is opposite your velocity. To make me accelerate downward, my downward force has to be bigger. So there would have to be a net force down, and the only down force is weight. So Fg is the bigger force. Alright, write a Newton's second law equation for the person in the elevator that includes the forces in your diagram. So because this is review, let's not skimp. We'll start with F net equals ma, and then let's do both F net x and F net y. F net x equals ma in x, F net y equals ma in y. As far as I can tell, there are no net forces in x, so equals m times ax, and we could even from that decide ax is 0 if we wanted to, but really we could stop here. No net forces in x. Alright, now in y, there is a normal force up, and there is a weight down, and that is equal to m a y. And really, that's the equation. I've written it. So there we go. We've written a Newton's second law equation. That would be satisfactory. If we wanted to, and since this is review, let's go ahead. We could then solve for ay. So let's divide by m on both sides. And I get n minus Fg, normal force minus weight, divided by the person's mass, equals that acceleration in y. Yeah, there we go. So if you were asked to find acceleration, that's how you do it. And we can know, since the person is slowing down like the problem said, that this would be negative. We drew above that our acceleration is down. And that's something to know. So if you're slowing down, that means you have an acceleration opposite velocity. Slowing down equals a opposite direction of v. Your acceleration is in the opposite direction of your velocity. So in this case, the elevator had velocity up, but was slowing down, so its acceleration was down. Alright, if you didn't understand any of that, be sure to rewatch it, because this is really the last chance before the test. We'll have some time for questions tomorrow, but this is it. Got to be ready. Alright, have a good night, and see you tomorrow.